right, how's everyone feeling?
Totally awesome, sir.
Wonderful. So here we're looking at a person riding on a low friction turntable, and they're holding two dumbbells of 5 kilograms each, extending their arms out. And the radius between the dumbbell and the axis of rotation is 0.80 meters. And originally the person's spinning around about once per second, which is 2 pi radians per second, which is 2 times 3.14 radians per second, which works out to be 6.28 radians per second. The question is, when they bring those dumbbells in to a smaller radius of 0.40 meters, what happens to the angular velocity? Now, we know that a torque produces a change in angular momentum. But no one's coming from the outside and putting a torque on these people, on this person here. So since there's no outside torque and no one's coming in and giving them an additional nudge in either direction, we know that the angular momentum is going to stay constant. But we do know that the moment of inertia is going to be decreasing, because moment of inertia is calculated by mr squared if you're dealing with like a point mass like out here. We're going to be neglecting the mass of the person. We're neglecting that mass. And we're only focusing on the mass of the barbells. And if the radius is decreased, we know that the moment of inertia is going to decrease. So momentum is mass times velocity. Angular momentum is moment of inertia times angular velocity. If this stays the same because there isn't any torque put on it, this decreases because the radius decreases. What does the angular velocity have to do?
It's going to have to increase.
It's going to have to increase. Since angular momentum is conserved, we could say I times omega over here, initially, is equal to I times omega over here, finally. Now the moment of inertia is mr squared, but we have two of those masses. So it's going to be mr squared, but each of them have the same mass and the same radius, so we could just multiply that by 2 because there's two of them. And that's going to be multiplied by the initial angular velocity. Likewise over here, we still have two dumbbells, but they're going to be at a shared smaller radius, so it's going to be 2mr squared, but this is going to be a final radius, and this is an initial radius times omega f. So 2 times 5 kilograms times 0.80 meters, and that gets squared, times 6.28 radians per second equals 2 times 5 kilograms times 0.40 meters squared times the final velocity. Now we could just like crunch out all the numbers, but do you recognize like some major simplifications? Jason?
The 2's and the 5's can just cancel out.
Yeah, that 2 and that 2 cancels out. And this 5 kilograms and that 5 kilograms cancels out. So it really just boils down to r squared times omega equals r squared times omega. And did anyone crunch that out and actually get an answer for omega? What'd you get? Let's go to Chris.
25 radians per second.
And notice that's like nearly quadrupling when the radius was just cut in half. And that has to do with the square here. So you end up spinning way, way faster.
Concerns.
Yes?
Can we look at tangential velocity for this? It seemed like it wasn't equal.
Well, that's a good question. All right. Excellent question. Let me just pause this here.